Welcome to another video in the series about the C7000 compiler. This video introduces a feature unique to C7000 called the streaming engine, including why and how to use it from the compiler. My name is George Mock, and I'm your guide. What is the best way to load a full vector of data from memory into the C7000 CPU? Well, by using the streaming engine. The streaming engine also reduces the number of instructions needed to compute an address. And for an important loop, reducing the number of instructions in that loop means it's going to run faster. How does all of this work, and how is it programmed? That's what this video is about. Throughout this presentation, the abbreviation SE stands for the streaming engine. There are some similarities between an SE and an SA, where SA stands for a streaming address generator. And those are, an SE is a multi-dimensional offset computation engine, and it compute offsets for up to 6 dimensions. If you've not seen this before, I recommend you go watch the video on the streaming address generator. It's explained in more detail there. I'll also flesh it out in the examples. There are also some differences between an SE and an SA. An SE presents data at up to vector width bits per CPU clock and a holding register, which means it's read-only. Remember, with an SA, you can perform both reads and writes. With an SE, read-only, okay? Furthermore, data in the holding register is zero-filled as needed. Now, I admit this is probably the most confusing bullet on this slide right now. I will make this clear in the examples. Current C7000 variants provide 2 SEs, and they are called SE0 and SE1. A high-speed connection between the CPU, functional units, and L2 memory is a big part of why the SE was put in the system in the first place. In this bullet up here, I said presents data at up to vector width bits per CPU clock. Among the conditions that have to be met to meet this performance goal is you have to be reading from L2 memory. At this point, I'm just trying to make you aware of this connection between L2, getting a high-speed connection, and the SE. This sort of thing is beyond the purview of the compiler and its related documentation and videos. That sort of information will be found in the software development kit, the SDK that you use for your particular system, its related documentation and examples, and so on. So that's where you need to find that information. The main part of this video is 3 examples. Each example builds on the previous one, so focus on understanding the last example. If some small detail in the first 2 examples is confusing, it's probably best to just let that be, and it'll probably resolve itself. And if not, you can always go back and view it again. Each example contains one function, and that function sums an array of length integers and returns it. Never hesitate to pause the video to closely view an example. It may make sense to view parts of the video in a different order than I record them. Take screenshots if you need to. I mean, whatever it takes to learn the material is what's important here. Among the presumptions that I'm making as I'm going through these examples is that I presume you understand the content of these earlier videos in the C7000 compiler video series, and their titles are Streaming Address Generator Part 1 and Part 2, and Scalable Vectors. Welcome to the first example. This example is a copy of the one used from a previous video, and that video is Streaming Address Generator Part 1. This is the second example in that video. So I'm going to go through it here pretty briefly. If you need to know it in detail, I recommend you go watch that video where it is described in extensive detail. So the interface to the function is it accepts an array of integers, length integers, adds them up and returns it. This variable right here sums all the values up 4 at a time, so that is a vector of 4 integers. That's the type. So this thing works 4 integers at a time. Lines 9 through 12 configure an SA. Line 15 opens an SA. Lines 18 and 19 compute the sum. 4 integers at a time. This variable here. This is the function that you use to have the SA return the address of that value. The asterisk is how you say load it. And the ADV says advance. Lines 22 through 24 are how you add in the last value. In the case where length is not an even multiple of 4, there are going to be a few values to add in. And this is how you do that. That's described in detail in that previous video. And then we close the SA. And then the last few lines, lines 30 through 34, they're mostly scalar. They're adding up all the values inside the vector of 4 integers in semi4 and then returns it. All of the functions, all of the examples in this video have very similar code at the end, so this is the only time I'm going to describe it. Now the reason I started with this particular example is that it's a good point of comparison for the first example that uses the SE. Next I'll open up the first SE example. And the purpose of this example is to show using the SE with a fixed width vector, which is pretty similar to what's going on with the SA in the example on the left. So that's why it makes for a good initial comparison. So the first thing I like to do is the things that are the same, I like to try and line them up. So that looks pretty good. So sum by 4 SE, we are continuing to sum up all the integers in this array 4 at a time, but instead of using the SA to do it, now we're using the SE. So the initial code, lines 5 and 6, no different. Lines 9 through 13, we're configuring an SE, which has some similarities to configuring an SA, but it's not identical. Notice how there's an SE and the letters SE in several places where you see the letters SA in the code on the left. Okay, and I named the structure that we're creating and changing some of the fields in it and SE params and not SA params as I did on the left. But the general role of each field, veclen, dim format, dimensional format, and iCount, is the same between the two, so I'm not going to describe those fields. And yeah, the way you initialize it to all defaults by calling a function, that's the same. It's a different function in SE something function and not SA. So there's only one new field to describe, and that's this one, ELE type. And what you're saying is, what is the size of a single element in the vector? Well, this is a vector of 4 integers. An int is 32 bits, and so that's why you choose this particular type. It's an enumeration value to initialize this field with. All right, so now that the SE configuration is set, opening it is similar to opening an SA, but there's one very important difference. An SE open, of course, it refers to the parameters that you configured, in this case on lines 9 through 13, but it also refers to the base address that the SE is going to start with. And in this case, the base address is the same as that base address passed in as an argument to the function. So the first value that the SE gets from memory is going to come from that address, and then it's going to advance to the next value in a manner similar to an SA. Okay, and that's what's happening here in lines 19 and 20. They're similar to the same lines on the left. We're calling SE0 ADV instead of SA0 ADV. And just like before, the 0 in the name has to match the 0 in the open. And that continues to be the case with all the functions. SE something functions called. That 0 has to match. The type is there for the same reason. In this case, you know, the SE gets a value in a holding register, and then when the compiler uses that value, well, what is the type of it that is coming out of it? And well, in this case, it's a vector of 4 integers, and then you don't notice how you use the asterisk on the left, because an SA returns an address. The SA advanced function returns an address. The SE0 advanced function returns a value, therefore there is no asterisk, and so you sum it into, you're accumulating it into sum I4, length divided by 4 times, because you're working 4 integers at a time. There is one value to add in at the end. That's happening here on lines 23 and 24. Now there is no function for the SE that corresponds to in the SA. You can say SA0 vpred, give me the predicate for the current offset. That's not a thing with an SE. Okay, SE is constantly giving you values, and when you get to the end, because you know the SE knows for itself this is the length, you know, and it's advancing because you're calling this, it's advancing through them. It knows when you've gotten to the end, it can work out what is this predicate on its own. Okay, so while you can do it this way, and by the way, I've tested all this code. I know it works. I've seen it work. You can compute it this way. It ends up being overkill because the SE is doing this for you anyway. So you can change the code, and I'm going to go ahead and do it live. So if I make some minor mistake, please be patient. But this is the way I like to comment out code. There are multiple ways to do that, but I like to do it this way. Every once in a while, leaving the old stuff behind becomes important. And actually, I've changed my mind. I should have done this all along. Oops. Should have put that in there. Okay. All right. Sorry about that. And what I'm going to change this to is and then yes. Okay. So what is presently lines 23 through 25, that's all been replaced by line 27. That computes the same thing, because all of this business with computing a predicate and then using the select, the SE has already done that for you. And remember how I talked about how for values in the holding register that are in effect masked out by the code similar to 24 and 25, those values are filled with 0. Okay, and so that's why it's okay to just add that to sum I4. Okay, there are ways to configure an SE up in here so that those values are filled with something different from 0. Okay, but I don't talk about that in this video. I just want to point out that exist. By default, for the values that in the case where length is not a multiple of 4, there are a few values that are in that holding register that should not be added in. So they're set to 0 in a manner sort of similar to how this is doing the same thing. But it's already done for you in the SE holding register, and this gets you that value. Notice how this doesn't advance, but this does. Okay. So that's all of this raises the question, well, couldn't you, similar to how the last example in Streaming Address Generator Part 2 increased the number of iterations of the loop by 1 and just kept going over that last one, could you do that? And the answer is yes. Okay. And I'm going to make those changes here, again, live, so I need your patience. One thing I did do, I cheated a little bit. I have the important code, I say the important, a significant amount of the code zeroed out down here. So let me make a copy of it. And I'm going to go put that in before the loop. And let me straighten this up. Oops. There we go. Alright, and now this is not going to be using length divided by 4 anymore. We're just going to use loop count. Okay, so now lines 18 through 20, compute the loop count. It starts with, the same old length divided by 4 that was there before. Okay, and then if length is not a multiple of 4, increment the loop count by 1. All right, this comment on line 22 is now wrong. Please ignore it. Sorry about that. Okay, and now we run loop count times using SE0 advance. And by the way, I've made another mistake. Let me correct that real quick. I'm going to move this. Okay. You don't want to execute this anymore. All right. You don't need this final accumulation, because if that's necessary, the loop's going to run one more time and this code will do it. Okay. So everything I've talked about, how if length is not a multiple of 4, that last load into the holding register of the SE is going to zero out the values that you don't want, and so it's okay to add that to sum I4, and all of this computes the same result. So that's it for the comparison between example 1 and example 2, the first example that uses the SE. I'm going to go ahead and close. Example 1, don't save changes, and I'll give you a look at it. And things are kind of a mess right now, so I'm going to go ahead and delete this, close these lines up, and like that. Okay, so for those of you who like to get a screenshot of the first example that uses the SE, this is a good time to do that, and then I'll advance to the bottom, here, and go ahead and take your second screenshot. Let's review the SE interface that was introduced in the second example. This is the type of a structure. An SE is configured with fields from this structure type. The function SE0open takes 2 arguments, a base pointer, memory reads start at the address given by that base pointer, and then a parameter structure of this type that has all the values in it for how to configure the SE. Opens it, gets it ready for business. The function SE0 type is an input to the function SE0. It returns a vector of data according to that type, 0 filled as necessary. And I talked about that in the second example, how that 0 fill behavior, 0 fill behavior. And then SE0 ADV stands for advance. It returns the same result. It also advances SE0 to the next offset. SE0 close, it's very clear what that does. Every operation, such as SE0 close, has variants for SE0 and SE1. So there is, for instance, a function named SE1 close. Now I will open up the third example. The purpose of the third example is to show how to use the SE in combination with scalable vectors. So the first thing I'll do is line up things that are similar. Okay. Okay, that's pretty good. So, one change to note is that in example 3, we include C7x scalable.h in addition to C7x.h, and C7x scalable.h has all the utilities and types required for scalable types. The interface to the functions is the same. They both add up all of these integers together and return that result. Setup code for scalable vectors, there's a little bit more to do. On line 6, I have this using directive. It turns out this type, C7x, this type, C7x, intvec, occurs lots of times in this code, and it just made it more readable to create this type equivalent, and you can see how it's used in several different places in the code. It makes the code more readable. This is the variable that accumulates the sum. It is a scalable vector. SV stands for scalable vector. In this case, it's a scalable vector of integers. This is how you capture how many elements are in one vector in this scalable vector. And keep in mind it changes as you build for different C7000 CPUs, and they have different vector widths. This will automatically adjust to hold the maximum number of integers that you can put in that vector, however large it may be. So the configuration of the SE parameters, there are some similarities, but a couple of differences to point out. So for veclen, you use this utility from C7x scalable.h, and you use it in this type traits way to get that value, because, you know, of course, with a scalable vector, you don't know the veclen at build time. Well, I'm sorry, at the time that you're writing the code, you don't know the vector length. At build time, this is a known constant, but this is how you get at it. Same thing with the element type. There's a service in C7x scalable.h for getting at the element type, and here's how you do that. Opening up the SE is the same. You know, pointer is the base address that you're going to start at, and these are the parameters for configuring the SE. Computing the loop count is the same. So if the loop count is not an even multiple, well, I say the same. Over here you're dividing by 4, and on the right you're dividing by veclen, whatever that may be. If the number of integers you're adding up is not an even multiple of veclen, then we're going to run the loop one more time. Okay? And then the code on line 27 and lines 27 and 28, that's doing the actual accumulation, summing up values into some SV, just like this. This is how you get a value from the SE and tell it to advance to the next one in a scalable way. This 0 here is how you say which SE you're using. It's got to match this 0 right here. Okay. Then IV underscore T is the the vector, the type. It is a scalable vector of integers. Okay. and same type as SUMSV. And then the rest of the code is very close to the same. Yeah, the close and then the final sum, that's all the same, so nothing terribly interesting there. So it ends up being pretty close. The fixed width vector way of doing it and the scalable vector way of doing it, there's a little bit of setup difference. And after that, things are pretty much the same thing. So let me close the second example. And give you a look at the code for example number 3, the one that I want you to understand the most. This is the way I think it makes sense for most of you to use it in the field most of the time. So here's the first part of the function, and I'll go down a little bit. There's the rest of the function. I want to review the interface for working with the SE with scalable vectors. The first one is this one, C7X SE VecLen, and its input is a type, and you get at it with this type traits type code. This is for configuring the VecLen field and an SE parameter structure, and for the type it would be a scalable vector type like C7X IntVec. This next one is similar, but it's for a different field, for configuring the ELE type, element type field, and an SE parameter structure. So this just the spelling difference here, otherwise it's the same as the previous one. The third one, this is how you, and I actually didn't use this particular one in example 3, but I'm going to show it anyway. So this is a template class. The inputs are, SE num has to be 0 or 1, and the type is the same as the previous guys. And then this is a member function in the class, get. This is how you, read the value in the holding register in an SE. So it's similar to SE0 as I shown in the previous interface, as shown in example 2. I already said the SE number is limited to 0 or 1. And then this last one is the same, except for you say get ADV for get the value and advance the SE to the next one. So similar to SE0 ADV in example 2. I want to close this video with 2 references. The first one is to this web address here. That's kind of long, so I recommend you search the internet for C7000 compiler. I've tried this search with a few different search engines, and I get this result. I get this web address as the first result. However you get there, you're at the home page for the C7000 compiler. This is where you can download the manual. Download the compiler, access the manual, and more details like that. The second reference is to e2e.ti.com. This is for customer questions on any TI product, including the C7000 compiler. If your question is related to the compiler, it will be answered by me. Thank you for watching this video in the series about the C7000 compiler.